Okay, maybe we will discuss about the reagents. Okay, more particularly the question and answer section of on reagents. So, what are the reagents we discussed up to this? We discussed about NBS, DCC, DDQ, Prevost, Woodward, and TMS, Raninical, polypropylene PPA. Okay, and let's give an entry. Right. Okay, the first question here, the questions are in random. It's not particularly about the reagent, but it is related to all the reagents. And one more thing, so these questions are I have taken from the BCU examination question papers. So this is one N, N dimethyl benzoic acid. N, N dimethyl, which position? 3 position. 3 N, N dimethyl benzoic acid. When it is treated with diazomethane, here there will be a question mark. So what you need to do? You need to predict the product and write the mechanism. If you want to predict the product, you can write this diazomethane as CH2 minus N plus N triple bond N. So here CH2 minus, it can act as a nucleophile. That is the reason it can pick up this proton. So once, and you can observe that there is a positive charge on the nitrogen. So that is the reason this bond pair is taken up by nitrogen. Then this bond pair, the bond between the oxygen and the hydrogen, will form a new bond with this carbon. So that is how a ester is obtained. Let's give an entry. Okay, that is how ester is obtained. So acid is converted into ester, more particularly methyl ester, when an acid is treated with diazomethane. So if you are looking into that, this is a reaction only. That means product means you have to write an ester. So if you are looking into the mechanism, initially the anion will pick up this proton, convert CH2 into CH3. So later on, the carboxylate anion react with this carbon when this bond pair is taken up by nitrogen. So that is how ester is obtained. So one more question here, how do you convert the benzoic acid into phenyl acetic acid? How do you convert benzoic acid into phenyl acetic acid? So give reagents and mechanism. That is only the question. So you need to write a benzoic acid. This is the structure of benzoic acid. And by using a diazomethane, it's a reagent, you can convert a benzoic acid into phenyl acetic acid. What is happening here? Higher homologous carboxylic acid is obtained. Insertion of CH2. So insertion of CH2 is possible through the alpha diazo compound. This is a alpha diazo compound. So now let's look into the mechanism. So benzoic acid. So benzoic acid, when it is treated with a compound called chlorinating agent. So what are the chlorinating agent? Thionyl chloride is a chlorinating agent. Phosphoric POCl3 is a chlorinating agent. So using the chlorinating agent, one can convert a carboxylic acid into acid chloride. Once the acid chloride is obtained, there will be a reaction with diazomethane. So diazomethane is a liquid. Of course, benzyl chloride is also liquid. Okay. What will happen? This anion is attacking here, and there will be a new bond formation between this carbon and this carbon. A intermediate is obtained like this. Afterwards, the anion, so the anion went over an oxygen, no, that will come back. So that means this anion can come back. So when this anion came back, then this Cl is a living group, it will go out. So once the Cl is going out, then the obtained compound is called alpha. This position is called alpha. Why? Because this is a functional group, this is a alpha. Alpha diazoketone is the compound. Alpha diazoketone can react with one more molecule of diazomethane. What it will do? It will capture this proton. Capture means it will take up this proton, leaving behind the bonded pair. When leaving behind the bonded pair means this carbon attains a negative charge. That's what I have written is here as a CH2 minus. So at that position, this CH2 minus can come over here, and this N plus takes this bonded pair and going out. So that time this bond pair is coming and forming a bond here. So this is a concerted reaction because there is an involvement of 6 electron system. So this is 2 electron, this anion is 2 electron, and this 2 bonded pair is 2 electron, 6 electron system. There will be a conversion of alpha diazoketone into ketene. So ketene is a widely used intermediate. This ketene on addition of water gets converted into phenyl acetic acid. This is about 2-3 times in the BCU question paper. You can find that how do you convert a benzoic acid into phenyl acetic acid. So then I will take up one more reaction, predict the reagent and write the mechanism. So this is the cyclohexanone. So here the reagent you have to predict, and this is the one product, this is another product. Okay, so of course this conversion of a cyclohexanone to cyclohexene epoxide, and this one is troponone. Okay, troponone. A 7-membered ring with ketone is called troponone. If there is a double bond, tropinone. Then, so you need to write the mechanism how a higher homologous ketone is obtained. Again, here also you can observe that this is a 6-membered ring, this one is a 7-membered ring. That means CH2 is added. CH2 added means it's nothing but a Arnott Hystert reaction. Of course, in this also a Arnott Hystert reaction because you are adding CH2 between the carbonyl and benzene ring. And here you are adding a carbon between the carbonyl and CH2 group. So how this is happening? Diazomethane can react. How it is reacting? This can attack this carbon when this bonded pair is sitting on the oxygen. So now on the oxygen bonded pair is there, and there is a diazo group. This group is called diazo group, and this is a methyl group. So when this bond pair is come back, there will be a movement of this bond pair from this carbon to this carbon, 1-2 migration. So 1-2 migration, and this will go out. N2 is the living group, and that is how troponone is obtained. This is about, this is also asked nearly 2 or 3 times in BCU examination. Now I will take up one more reaction. So give an account of PPA in organic synthesis. Give an account of PPA in organic synthesis. So PPA means is nothing but a polyphosphoric acid. Polyphosphoric acid. So polyphosphoric acid is nothing but a combination of phosphoric acid and phosphorus pentoxide. So it is prepared. So PPA is prepared by stirring a mixture. By stirring means rotation. Rotating a mixture of phosphoric acid and phosphorus pentoxide. It is generally reported. Okay, reported or prepared. This PPA is generally prepared when it is required. PPA extensively used in various chemical reactions. More particularly, the more important of which is cyclodehydration. So that means the product will be cyclized product. but there is a involvement of removal of H2O. So PPA is nothing but it will act as a dehydrating agent. In some cases, PPA has been found to be effective where reagents such as sulfuric acid, HS, hydrofluoric acid, aluminum trichloride, etc. Some important applications of PPA are described below. So this is the one I am taking a amino. Okay, X is equal to amino or hydroxy or mercapto. Suppose X is equal to amino means it's called orthophenylene diamine. If X is equal to OH, then we can say that aminophenol. If X is equal to SH, then we can say that amino mercaptol. Okay, mercaptophenol. Okay, right. So what is happening when a amino or hydroxy or mercapto anilines react with carboxylic acid? There will be a removal of water. How the removal of water? OH from here, OH from here. Otherwise, yes. So it requires to removal of 2 molecules of water, OH from here, OH from here, and later on H2 from here and O from here. So that is how a cyclized. Cyclized means more particularly heterocyclic compounds are obtained. So this is a general example, and here I am taking a specific example when X is equal to NH2. So in this case also, what you can observe, PPA, it will act as a dehydrating agent. It will remove H2 and O. There will be a new carbon-carbon double bond between the nitrogen and this carbon. So that is how the purine is obtained. And in this case, it is possible to prepare benzoxazole, imidazole, and thiazole. So that means it's a general reaction, but in this it is possible to prepare benzoxazole, benzimidazole, and thiazole. But purine also it is possible to synthesize by employing PPA as the reagent. And it is also possible to prepare a ketone, aromatic ketones, diphenyl ketone. How? One substrate should contain a carboxylic acid, other does not require. So here what is happening? There will be a removal of water. So OH and H is going out, forming a diketone. Okay, ketone means a aromatic ketone compound. So this is about write a note or write an account of PPA in organic synthesis. So similarly, one can frame a question on give an account of ranitidine in organic synthesis. Give an account of ranitidine in organic synthesis. But here, preparation, how the ranitidine is obtained. So ranitidine, this is the NiH is called ranitidine. Sometimes people used to write that Ni bar H2. Okay, so it's called ranitidine. Some people used to write RaNi. RaNi also it's a ranitidine. So what will happen here? How the ranitidine is obtained? The ranitidine is obtained by the reaction of nickel aluminum halide with sodium hydroxide. So this NiH is the insoluble one, more particularly a what you call gray color powder. And this ranitidine should be stored in alcohol, and it should not be exposed to the moisture because it will catch fire. And NaAlO2, this is the soluble in water, it will go out. Hydrogen is a gas, it will go out. So the obtained ranitidine, when it is treated with alkene, it will convert a alkene into hydrocarbon. Similarly, the obtained ranitidine, when it is treated with alkyne, it will gives rise to what you call alkane compound. So alkane means alkene is converted into alkene. Alkene is converted into alkane. So overall, olefins can be converted into alkanes. Alkynes is converted into uh, alkanes, saturated carbon atom. Unsaturated ones is hydrogenated in presence of rank nickel, giving rise to saturated compounds. So one more thing, a aromatic compound. So this is the speciality about the rank nickel. So why? Because usually you can take any hydrogenating agent in presence of catalyst. Those catalysts does not reduce the benzene completely into a aliphatic one. So whereas the rank-nickel, hydrogenation in presence of rank-nickel, it is the one, it will convert a aromatic compound, benzene, into cyclohexane. What it means? It means that it is possible to convert a aromatic compound into aliphatic cyclic compounds. So benzene is converted into cyclohexane when a hydrogenated in presence of rank-nickel at 250. So 250 is the pressure of a hydrogen during the reaction. And I think you are aware that this is a naphthalene. So naphthalene at a low temperature means 150 degree, it is possible to convert a naphthalene into tetraline. Tetraline means reduction of two double bond. This double bond is converted into saturated, this double bond is converted into saturated, then such compound is called tetraline. Let's give an entry. Right. Okay. So that means naphthalene, it is possible to convert into tetraline at low temperature. The low temperature means 150 degree centigrade. Similarly, naphthalene at 200 degrees centigrade, what will happen? Completely means whatever the double bond present in an naphthalene is converted into decalene. Okay. And this type of S bond is called disulfide bond. So disulfide bonds can be cleaved by using hydrogenation in presence of rank-nickel. So hydrogenation in presence of other catalyst, disulfide linkage cleavage is not possible. Disulfide cleavage, it is possible only in presence of rank-nickel. So what hydrogen will be added to here and there. So two molecule of mercaptan is obtained. So this is one mercaptan, this is another mercaptan. And then that means disulfide links can be cleaved. And nitro groups can be converted into NH2 group by doing hydrogenation in presence of nickel catalyst. Halides, replacement of halide with hydrogen, it is possible in presence of rank-nickel, giving rise to hydrocarbon. So what and all it is possible to uh, uh, rank-nickel application in organic synthesis. So olefins or double bonds can be converted into saturated, triple bonds can be converted into saturated, aromatic compounds converted into cycloalkane products, and then disulfide can be converted into thiols, nitro compounds converted into amino, halides can be converted into hydrocarbon. So here I am taking a general example, but these two are the specific example. Of course, these two are also specific example. So overall, what you need to remember, hydrogenation means it can convert unsaturated into saturated, it can convert aromatic into cycloalkane, it can convert the disulfide into thiol, and nitro into amine, and halides into hydrocarbon. So next I am taking one more question, that is TMS chloride. What is TMS? Trimethyl silide chloride. Trimethyl silide chloride, so several times asked for the 2 marks. So TMS chloride is an efficient reagent for the cleavage of uh, an efficient ether. That means TMS chloride is used in the cleavage of ether. So ether means ROR dash. R and R dash may be a same group or a different group. So that means TMS chloride is used to cleave the ether linkage. So why? So that explanation you need to give. The explanation means what is happening here, there will be a new bond formation between the silicon and oxygen. And similarly, there will be a new bond formation between the alkyl or aryl group with halides. So what is the one more thing you need to remember? The bond formation between the silicon and oxygen is strong compared to the bond formation between the silicon and other elements such as carbon and halides. So because of that, this reaction proceeds. So what you need to remember, what you need to explain here, the bond formation between the silicon and oxygen is strong compared to the other bonds. That is the reason TMS chloride cleaves ether and giving rise to silyl oxy, alkyl silyl ether. So alkyl or aryl silyl ether as the product, and alkyl halide as the byproduct. And one more question. So this is again a 3 marks question or 2 marks question. So what you can observe that give the application of 1,3-dithiene in a organic synthesis. So but you can mention anything. But before that, with respect to the 1,3-dithiene, you need to recall that a electrophilic carbon center is converted into nucleophilic carbon center. So this conversion, reversal of polarity of the electrophilic nature of carbonyl carbon to the nucleophilic nature is called umpolang. Okay. So, and what is happening here, how we are converting a electrophilic carbon to the nucleophilic carbon. So we are converting a carbonyl compound by treating with 1,3-propane dithiol in presence of trifluoroborane. So what will it will form? It will form a dithiene, 1,3-dithiene. And the butyl lithium, what's the role of butyl lithium? Its role of butyl lithium, it will capture this proton, forms an anion. So that is how electron deficient carbonyl carbon is converted into electron rich carbon. Okay, and these 2-litho-1,3-dithiene widely used in organic synthesis, and it will react with the carbon electrophiles as well as other than carbon electrophile. It also react with nitrile, halides, esters, carbonyl compounds, and also it will react with carbon dioxide. Okay, so that is the reason this is very much useful in organic synthesis. Once the required product is obtained, it is also possible to cleave the dithiene by treating with mercury chloride or silver chloride or cadmium carbonate. Okay, this is about 1,3-dithiene. And let's give an entry. Okay. And here, how do you achieve the following conversion? So what you can observe that a formaldehyde, when it is treated with 1,3-dithiol, you will get a 1,3-dithiene. Formaldehyde, 1,3-dithiene. A dithiene, how it is possible to convert into cyclobutane, cyclobutanone? So that is the question. So question is, how do you achieve the following conversion? And in a bracket, it is mentioned that may require more than one reagent. So let's look into the how this it is possible to convert 1,3-dithiene into cyclobutanone. So you can observe that this is the one. When it is treated with butyl lithium, the proton present here is captured, forms an anion. That anion react with this carbon and Br will go out. Intermediate is obtained. So the intermediate, again it is treated with butyl lithium. So what butyl lithium will do? It will react with the proton present on this carbon, forms an anion. That anion react with this carbon and Cl will go out. So that is how a bicyclic compound is obtained. This bicyclic compound, when it is treated with mercurous chloride, mercuric chloride or mercurous chloride. So what will happen? There will be a dithion cleavage forming a ketone. So this is how the 1,3-dithiene is converted into cyclobutanone. And here write the reagent. So here you need to write the reagent and here you need to write. So before writing, what you need to observe, there is a conversion of 1,3-dithiene into hydrocarbon. Hydrocarbon conversion means disulfide cleavage. Disulfide cleavage means raninical. Hydrogenation in presence of raninical, it is possible to convert a cleavage of dithiene, giving rise to hydrocarbon. And what is happening here from here to here? Dithiene cleavage. Cleavage in the sense it should be treated with mercurous chloride or silver chloride or cadmium carbonate. So what there will be a cleavage of this and giving rise to ketone. Let's give an entry. Right. Okay, so this is, that means here just it's a 2 marks question. You need to mention reagent here as a hydrogenation in presence of raninical, and here the reagent is mercuric chloride or silver chloride or cadmium carbonate you need to mention. From here to here it's a deprotection of dithiene. From here to here it's a hydrogenation, addition of hydrogen, and there will be a removal of thiol group. So I am taking a similar kind of one. Again, I am taking one more example. So here, this is the question. Predict the product of the following. So that means here one question mark, here and one question mark. So what are the reactants? A cyclohexanone, cyclohexanone, and it is 1,2-dithiol. So this is not 1,3, it's a 1,2-dithiol. So overall, a dithiol will react with this. How? H2, A2, here one H, here one H, O is going out. So there will be a new bond formation between this sulfur and this carbon, this sulfur and this carbon. So that is the question mark. In this place you need to write. That means this is the product. So, and this raninical means addition of hydrogen, where it will add one hydrogen here, one hydrogen here. These two sulfur will go out. So that means what is converted? A cyclohexanone is converted into hydrocarbon. So this is called Mosinot reaction. Mosinot reaction means conversion of a carbonyl compound into hydrocarbon is called Mosinot reaction. So with this, I will take up one more reagent. I think you are aware that halide. Okay, Chavosi. Okay, it's a halide. So what will happen? Halide will act as a source of CH2. So what will happen? A double bond. Okay, means carbonyl. Carbonyl compounds on reaction with halide, so it will give you cycloproponated product. So here there is a question mark. Then what you need to write? You need to write the product. How you can write? You can start with the halide. This is a similar to the CH2 is the halide, but here methyl, okay, ethyl source. CH3, CH2 minus, ethyl source. So what will happen here? Okay, right. So there will be this anion will react with this carbonyl carbon. When there is a reaction between the anion and this carbonyl compound, there will be a formation of intermediate like this. Then afterwards, the base can capture one more proton from here, forms an anion. That anion can attack this carbon and this bonded pair. Along with this bonded pair, DMS will go out. DMSO is the byproduct. And what is this? It's a cycloproponated product. So overall, what you need to remember, so I think here small changes you need to note down. So there should be oxygen. Where oxygen? Okay. Here there should be oxygen, no? So you need to mention oxygen. Oh, it's not reacting with the carbonyl carbon, but it is reacting with the double bond. So what it means? It means that if there is a alpha beta unsaturated carbonyl compounds, in such cases the halide react with the double bond, but not the carbonyl oxygen. That's what you need to remember. So the product is propane derivative, but not the epoxide. That's what you need to remember. And then citing a suitable example, explain the Corey-Chavosi reagent in organic synthesis. That means it is asked for the 5 marks question. Okay, this is the application part of the Corey-Chavosi reaction, and it is asked for 3 marks question. But this one is it is a 5 marks question because citing a suitable example, explain the use of Corey-Chavosi reagent in organic synthesis. So here I am taking 3 examples. Trimethyl sulfoxonium iodide is a Corey halide. Trimethyl sulfoxonium iodide in presence of potassium tertiary butoxide, it will form a halide, Corey halide. That Corey halide act as a source of CH2. That CH2 will form a bond between the oxygen and carbon, forming an epoxide or oxirane. Once the epoxide or oxirane is obtained, there will be a reaction between this oxygen, maybe a lone pair or the bond pair will form a new bond here, and this epoxide is converted into hydroxy group. And later on, there will be a removal of water. So what we can say that cyclodehydration, cyclization, cyclodehydration converts a hydroxy epoxide into phenyl benzofuran. 3-phenyl, 3-phenyl benzofuran is the product. And a skip base, this type of compound, skip base. Okay, this skip base, when it is treated with trimethyl sulfoxonium iodide in presence of potassium tertiary butoxide, here DMSO is the solvent. There is no role, DMSO role in this particular reaction. So this will act as a source of CH2. CH2 will add to a new bond formation between this carbon as well as this nitrogen. That is how azirine is obtained. So name of this compound, this 3-membered ring with nitrogen is called azirine. Okay, so once the azirine, then what is the name of this compound? 1, 2, 3. Okay, 3-phenyl, 1,3-diphenyl azirine is the name of this compound. And here also you can observe that a ester compound and a double bond. So double bond means alpha beta unsaturated ester. Alpha beta unsaturated ester when it is treated with Corey halide. So what is Corey halide? Corey halide is a trimethyl trimethyl sulfoxonium iodide. So it will act as a source of methyl group. There will be a new bond formation between this carbon and the source of carbon of Corey halide, and forming a cyclopropane ring. So these are the 3 examples I took for explaining the Corey halide in organic synthesis. That means it is possible to prepare heterocyclic compounds and also it is possible to prepare a cycloproponated product. So here with this, I'm going for LDA. LDA, you know that lithium diisopropyl amide. Lithium diisopropyl amide is a strong base, but not the nucleophile. What it will do? It will only capture the proton, forms an anion. That anion can react with the electrophile. So electrophile may be a TMS chloride, or maybe a carbon electrophile, or maybe a other than carbon electrophile. And here one more thing you need to remember. So what is the forming? The forming one is ene, means silyl ether. Ene silyl ether is the product if you are using trimethyl silyl as a electrophile. So that means LDA capture this proton, forms an anion. That anion can come over here, and this bond pair will react with the silyl, and Cl will going out. That is how product is formed. And here, this is again important question, many times asked about this. So here, one should explain in the form of kinetically favored intermediate and thermodynamically favored intermediate. So that means a 2-methyl cyclohexanone. 2-methyl cyclohexanone, when it is treated with sodium hydride followed by TMS chloride. Sodium hydride, what it will do? It's a strong base. So this strong base capture this proton. Okay, so that means it leads to the thermodynamically favored enolate. That thermodynamically favored enolate react with silyl and forming a compound like this. Okay, this is a thermodynamically favored product. And LDA, it's a strong base, but it is what it will do? It will capture a enolic proton, methylene proton, whereas this proton is called methane proton. Methane proton is captured by sodium hydride, whereas methylene proton is captured by LDA. So that means here there is a double bond, and this bond pair react with this silyl compound, forming kinetically favored enolate. This product is formed through kinetically favored enolate. This product is formed through thermodynamically favored intermediate. So what you need to remember, LDA means it always give you a kinetically favored product. Other than LDA means it will give you thermodynamically favored intermediates. That's what you need to remember. So with this, I will go to the next slide. So here I am taking one more example, but I am not taking a what is called as TMS chloride, but name of this compound is called propionyl chloride. Propionyl chloride is also called as propargyl chloride. So what will happen? LDA, it will capture this proton here, and this forms an anion. That anion react with this carbon. When it is reacting with this carbon, this bonded pair is coming over here, Br will go out. So that is how a product is obtained. And here I'm taking few more examples of LDA. So here you can observe that this is CH3 proton, means methyl proton, and this carbon one is called what you call methylene proton. And LDA, it's a strong base. So what it will do? It will capture a proton. Where it will capture? It will capture a proton here, forming a double bond here. That means this is an intermediate, and the lone pair or the bond pair can react with this carbonyl carbon, and forming a compound like this. How it will react? That means the bond between the oxygen and lithium can come over here, and this can picks up and form react with this uh, electron deficient carbon. So that is how a product is obtained. And here again, I'm taking, I think you are aware about what is called as preparation of alpha beta unsaturated carbonyl compound. So it is also possible to prepare alpha beta unsaturated carbonyl compound starting with carbonyl compound. So these two are carbonyl compound, but this one is alpha beta unsaturated. That means this position is alpha, this position is beta. There is a creation of double bond. So the creation of double bond is possible. How it is possible? So this moiety, when it is treated with LDA, LDA selectively cleaves this proton, forms an anion. So that anion can react with this CH2, Br will go out. So then afterwards, what will happen? That when it is treated with hydrogen peroxide, okay, hydrogen peroxide, so there will be a removal of anion formation, and that removal of water and giving rise to double bond here. Okay, so similarly, what you can observe, this is a lactone. This carbon is called enolic carbon. This this proton is called enolic proton. This proton, when it is treated with LDA, forms an anion. That anion react with this electrophile. Br will go out, and this is how a product is obtained. So now I will take up one more question. The question is on the Woodward hydroxylation. Woodward hydroxylation means reaction of double bond or olefin with moist silver acetate or silver benzoate in presence of iodine. So what is the product here is forming? The product obtained one is a cis hydroxylation. Cis hydroxylation is possible with Woodward reagent. What is Woodward reagent? Woodward reagent is moist silver acetate, moist silver benzoate in presence of iodine. So let's look into the mechanism. So a double bond first react with the iodine. How it is react? The lone pair present on the iodine can form a bond with this electron deficient carbon. Why it is electron deficient carbon? Because this bond pair are involved in a new bond formation with iodine. Why this bond pair is involved in iodine bond formation? Because this I is going along with this bonded pair. So what you can observe here, there is a involvement of 6 electron. So lone pair is 2 electron. This is another 2 electron. This 2 is another 2 electron, 6 electron involving. So it is a concerted reaction and forming an intermediate like this. At this time, the lone pair or the bond pair of silver acetate or silver benzoate form a bond with this carbon. But what it will do, it won't attack from iodine side, it will attack from the opposite side of the iodine and forming a intermediate like this. At this moment, we know that iodine also a better leaving group. How it will go? The lone pair present on this oxygen can form a bond here and iodine will go out. At this moment, since there is a involvement of lone pair, this bond pair is converting as a lone pair, forming a positive charge on this carbon. Since the reagent contains moist means water, the lone pair present on the oxygen can react with this carbon. Okay, then what will happen? This bond pair is coming over here and this bond pair can pick up a proton. So that means hydroxyacetate is the intermediate. This hydroxyacetate on saponification means treating with sodium hydroxide or potassium hydroxide. So what it will do, there will be a cleavage of acetate into alcohol. So what is the product obtained? Cis diol. Cis means same side hydroxy group compounds are called cis diol. Okay. So this is what it means by Woodward hydroxylation, it is possible to get cis-diol when an alkene is treated with moist silver acetate in presence of iodine. So suppose if you are looking into the Prevost hydroxylation, so Prevost hydroxylation means there won't be a moist. That means there won't be reaction of water in the reaction. That means dry condition. So dry condition means dry silver acetate, dry silver benzoate in presence of iodine. Olefins are alkene on reaction with dry silver acetate in presence of iodine gives trans diol. So it's called Prevost hydroxylation. If you are looking into the mechanism, the first step is same as usual in the Woodward hydroxylation, and the second step also is same as usual in the Woodward hydroxylation. But in the third step, there won't be water attack to the electron deficient. But instead of that, what will happen? The acetate, dry acetate can capture a proton. Since there is a capture of proton, what will happen? There will be this bond is taken up by acetate itself. And what it means? It is possible to form diacetate. So in the Woodward hydroxylation, hydroxyacetate is the product, intermediate, but here diacetate is the intermediate. Dry acetate on saponification, so it will give you trans 1,2-diol. So this is about what is called as Prevost hydroxylation and Woodward hydroxylation. So overall, the difference between the Woodward and Prevost means in the Woodward you will get cis-diol, but there will be a moist silver acetate. In the Prevost, dry silver acetate or dry benzoate, but a olefin is converted into trans diol. That is the difference you need to remember. So with this, I will go to the next reagent that's called NBS. NBS, you know that what it will do? It will capture allylic proton. Allylic proton. Here in this NBS reagent, you should be able to find out which is allylic carbon, which is allylic proton, which is enolic proton, which is enolic carbon. So if you are able to find that, then writing the product is easy. But in this is called a methyl proton. This carbon is allylic carbon, and this proton is allylic proton. So between this is methyl and this is methylene. So methylene is more acidic. That is the reason this proton is captured and replaced by Br. So that means here the Br should be right as a product. And then here this proton is called enolic proton. The enolic proton, what it will do? Enolic proton is captured by NBS, replaced with bromine. So that means this H is replaced with Br. This is the one. And in this compound, you can observe that this carbon is called allylic carbon. This proton is allylic proton. This proton can be replaced with Br. So here benzyl peroxide is a radical initiator, and this is a radical mechanism is involved. And in this steroid, it's a steroid. So what will happen? There is a double bond. This carbon is called alpha carbon. This proton is called allylic proton. This proton is replaced with Br from NBS. That will be the product. So you can observe that Br here and Br here. And then predict the product and write the mechanism. So a double bond is there, but here you can observe that NBS in presence of a phase transfer catalyst. This is the phase transfer catalyst. So phase transfer catalyst means the solvent should contain water as well as an organic solvent. In such cases, what will happen? NBS will act as a source of Br plus and Br minus. So that means addition of bromine to the double bond. So here addition of bromine, addition reaction takes place. The dibromo compound is obtained. So if we are looking into the mechanism, NBS, when it is treated with the double bond, it will give you bromonium intermediate. This bromonium, so what it means? It means that one of the NBS will act as a Br plus source and other Br will act as a Br minus source. So NBS in a polar solvent, it will give you a addition product. That's what you need to remember. Whereas NBS in non-polar solvent, carbon tetrachloride is non-polar solvent. What it will do? It will substitute hydrogen with Br. So this is the difference between the substitution and addition reaction. And here I am taking one more. It's called predict the product. NBS in presence of water. Okay, what is the product? The obtained product, when it is treated with sodium hydroxide, what is the product? So you need to predict the product. So for this product, 1 mark, for this 2 marks, 2 marks question it is. So what will happen? I think you are aware about the NBS. Okay, NBS H2O means polar solvent, addition reaction. So Br will form a bond over here, and how it will form? The lone pair present on this pi bond react with Br plus. Okay, succinimide is the byproduct, and there will be a positive charge on this carbon. Since there is a positive charge, the water molecule itself is attached to this electron deficient carbon. So that is how a bromohydrin. So bromohydrin is formed. This obtained bromohydrin, when it is treated with sodium hydride, sodium hydride is a strong base. What it will do? It will capture this proton. H2 gas is the byproduct. Once there is a capture of this proton, O is converted as an anion. That anion react with this carbon and Br will go out. So that is how cyclohexane oxide is formed. So this is about how the bromohydrin is formed, how the cyclohexane oxide is formed. Sometimes they will ask you what is bromohydrin. So that time you need to explain that a cyclohexene, when it is treated with NBS in presence of water, it forms a bromohydrin product. So that's what you need to remember. So now I will take one more question. Sketch the mechanism of formation of peptide bond by DCC. I think you know that DCC is a dicyclohexyl carbodiimide. It will act as a dehydrating agent. That means it removes H2O. How it will remove? So you can observe that this is a acid, this is a amine. So H from here, OH from here, and there will be a new bond formation between this nitrogen and this carbon. So what it means? Its amide is obtained. The H2O is taken by DCC. DCC is converted into DCU. This is the reaction. If you want to look into the mechanism, of course, this amide, since suppose R and R dash is an amino acid, then this amide itself is called as a peptide. Okay, so here 1 mole of N protected. This N is protected by using N protecting groups. N protecting group may be a Bach group. Bach means benzyl oxycarbonyl. Z group. Z group means Z group only benzyl oxycarbonyl group. Bach group means butyl oxycarbonyl group. F mark means fluorinyl oxycarbonyl group. So N may be protected using N protecting group. So N protected carboxylic acid. So you know that this carbon is electron deficient. The lone pair or the bond pair between the oxygen and hydrogen, it will react with the electron deficient carbon, and this bond pair can pick up this proton. So that is how O acyl, this group is called O, and this acyl, this group is called acyl. O acyl is an intermediate is formed. The O acyl intermediate react with C protected amino acid. Here C group of the amino acid is protected. So C protection may be a benzyl group is the best one. Then what will happen? The lone pair present on this bond will react with the acyl carbon. And this bond pair is coming over here. This bond pair picks up a proton. So that is how DCU is the product and a peptide or amide is obtained. So this is for the 5 marks question. How do you get a peptide? Explain with the mechanism. Okay, by using DCC as a reagent. Then here example, okay, it's a two reactant amino acid and means amino group and carboxylic group. When it is react with DCC, it will give you amide. So how 1H from amino group, OH from the carboxylic acid, that is taken by DCC converted into DCU. So this is again mechanism, one more mechanism. So this is a DCC. This in presence of proton, the lone pair can picks up this proton, and lone pair present on the nitrogen can picks up this proton, forms an intermediate like this. At this moment, the oxygen lone pair of the carboxylic acid or the bond pair can form a new bond with this electron deficient carbon. So that is how a O-acyl urea is obtained. Then the lone pair or the bond pair can react with acyl carbon, forming a peptide or amide. So this is about what is called as the application of DCC in peptide bond formation. So I will take up one more question. How the DCC is prepared? Give an example. So you know that DCC is obtained on treatment of N, N dicyclohexyl urea with mercuric acid. So mercuric acid here, it will act as a dehydrating agent. It will remove water. Means H here, and oxygen. It is going out. A DCC is obtained. Okay. And then here I am talking about one more application of DCC. Okay, OH and H, removal of water from the DCC, giving rise to anhydride formation. So mechanism, so this is the product and the mechanism. So this is a DCC in presence of proton, it will give you an intermediate like this, then carboxylic acid. Okay, the lone pair or the bond pair can form a bond over here and gives an intermediate like this. Then afterwards, O-acyl urea as well as another acid part, means nucleophilic part also, it is in the same molecule. So that is the reason lone pair or the bond pair can react with this O-acyl moiety, and this bond pair can come over here and this can picks up a proton. This part is going out as a DCU and the remaining part is converted as a anhydride. So anhydride means, more particularly, this compound is called this is pyran, benzopyran anhydride. Okay, and then I will take up DDQ. So this is the general reaction. So this compound is called DDQ. What is DDQ? Dichloro dicyano benzoquinone is DDQ. What its role? Its role is removal of hydrogen. Removal of hydrogen is called as dehydrogenation. So this is a substrate. So, substrate is converted into unsaturated one, saturated to unsaturated one. So this particular method is useful for the conversion of partially saturated compound into aromatic compound. So here I am taking, this is a partially saturated compound, 1,2 dihydrobenzene. So this H and this H is taken up by this DDQ, converted into DDQH. So we can also call as benzoquinone, hydroquinone. And this is the oxidized form, this is the reduced form. And dihydrobenzene is converted into benzene. So this is the general example. Normally, sometimes they will ask you very general question, write a note on DDQ, how it is useful in the organic synthesis. So here, this particular mechanism, this is called 1,1 dimethyl tetraline. How do you convert 1,1 dimethyl tetraline to 1,2 dimethyl naphthalene? Write its mechanism. And conversion. So here, what you need, here you need to remember, here there is a double bond, here there is a double bond. This means naphthalene is converted into tetraline. You need to suggest the reagent. What is the reagent? DDQ should be the reagent. So where should be double bond? Double bond should be in the reactant or the product. Double bond should be in the product, but because of removal of water. Removal of H2. Removal of H2 is nothing but a DDQ1. And this is the mechanism. This is called DDQ. And hydride, okay, H is going with along this bonded pair. H is going along with this bonded pair to add this oxygen. So when there is a new bond formation between this oxygen and this hydride, this bond pair is going over here, this bond pair is going over here, this bond pair will sit on this oxygen. This is an intermediate. Then what it will do, it will, this bond pair capture this proton, leaving behind bonded pair here itself. That means bonded pair will form a bond over here. That's called one double bond is formed. Later on stage, this hydride is shifted to one more equivalent of DDQ. And this anion picks up this proton and this bond pair is coming over here. So that is how a naphthalene is obtained, starting with tetraline. This is called tetraline. This is how a tetraline is converted into naphthalene. So this is partially saturated one. When it is treated with DDQ, the 1H from here, 1H from here is going out, forming a product called naphthalene. So, and this is the mechanism part. Okay. Okay. That's all. These are the questions asked in the main examination. And up to this, I have discussed a few questions, more particularly questions from BCU examination. And if you have any doubt, you can ask me. If there are no doubt, 1 minute, I will mark